All right, welcome back. Today, we're going to tackle a topic that gives so many of us headaches, vector integrals. But look, forget the confusing symbols for a minute. In the next few minutes, I'm going to show you how to see these not as some big, scary monster, but as a seriously powerful and, believe it or not, intuitive tool in your engineering toolkit. So, be honest. Have you ever looked at these symbols and just felt your brain kind of start to fizzle out? You are definitely not alone. These are probably one of the biggest hurdles in electromagnetism. But what if I told you they're all just different ways of doing one simple thing?
Because that's the big secret, really. The whole game is just about summing things up. So over the next few minutes, we're going to take these intimidating-looking expressions and turn them into simple, common-sense tools. We're going to completely pull back the curtain.
At its absolute heart, this is all an integral is. Seriously, before you get bogged down in all the rules, just burn this into your brain. An integral is just a really fancy way to add stuff. It lets you take a big, messy problem, slice it up into an infinite number of teeny tiny manageable pieces, and then just adds them all back together to get the total. That's it. Okay, so to make this idea really stick, we're not going to use a bunch of abstract math. Nope. We're going to use some real-world pictures that you can actually visualize in your head. Let's start with something simple, like going for a hike. So imagine you're hiking on a winding mountain trail. A line integral is basically like calculating the total effect the wind had on you for that entire trip. See, at every tiny step you take, the wind might be helping you, or it might be pushing right against you, or maybe it's just hitting you from the side. A line integral's job is to simply add up the wind's effect on every single one of those tiny steps to figure out its total impact over your entire hike. Okay, now for the next one. Picture a window screen during a rainstorm. A surface integral is like measuring the total amount of rain that actually passes through that screen. It adds up the little bit of rain flowing through every single tiny hole in that screen to give you one grand total. You'll often hear this called flux. It's all about flow through an area. And last but not least, think about a big puffy cloud. The electric charge inside that cloud isn't spread out evenly, right? It's clumped up in some spots and thinner in others. A volume integral lets you calculate the total charge tucked away inside that entire cloud. It does this by adding up the charge in every tiny microscopic cube of water vapor that makes up the whole thing. All right, so you've got the concepts down: hiking, rain, and clouds. Now, let's connect those ideas to the actual math, the language you're going to see in your textbooks. So here it is. This is our hiking integral. We use it to find the total effect or the accumulation of some vector field, we'll just call it A, along a very specific path, which we'll call L. Let's really break this down. That bold A, that's our wind field. The D, that's just one of your tiny steps on the path. Now the dot between them, the dot product, is a clever little tool that basically answers the question, how much of this wind is actually pushing me in the direction I'm going? It filters out any force hitting you from the side. And that big squiggly symbol, the integral, well, that's just the add it all up button. It sums up that push for every single step you take on your journey. And this one is our rain through the screen integral. It's designed to measure the total amount of a vector field, A, that's passing or fluxing through some surface, S. It's just like adding up all those raindrops. And finally, our cloud integral. Now, this one's a little different. See how there's no bold letters or dot product? That's because it's used to add up a scalar quantity, something without direction, like charge density, which is that rho v symbol, all throughout a 3D volume, V. And this brings us to a super important point, and honestly, this is a little detail that trips a ton of people up. It's about the nature of those tiny little pieces. Your tiny step, dl, it has a direction, right? And the tiny patch of your screen, ds, it also has a direction. It points straight out, perpendicular to the surface. But that tiny cube of volume, dv, that's just an amount, it's a number. It doesn't have a direction. So dl and ds are vectors, but dv is a scalar. Remembering that is absolutely key. Okay, that's enough theory. Let's get our hands dirty and see how this stuff actually works with a simple example. I promise, this is where it's all going to click into place. So here's the problem. We need to find the length of 1/4 of a circle that has a radius of 5. Seems pretty straightforward, but how do we prove it using this new integral tool? Well, this is a perfect job for a line integral, isn't it? We are literally trying to find a total length along a path. So all we have to do is add up the lengths of all the infinitely tiny little segments, all the dl's that make up this curve.
So let's get everything set up. Since we're dealing with a circle, using cylindrical coordinates just makes life way easier. In that system, a tiny piece of an arc, RDL, is just the radius r times the tiny change in angle, d phi. And we know our path is from an angle of 0 up to pi over 2, and our radius is a constant 5. We've got all the ingredients. So when we put it all together, our integral looks like this. The total length is the integral of dl. We just swap in what we know. dl becomes 5 times d phi, and we're integrating from our start angle, 0, to our end angle, pi over 2. And when you solve that super simple integral, you get 2.5 pi. And there you have it. We just used that fundamental idea of a line integral, summing up tiny pieces along a path, to solve a real, tangible problem. Pretty cool, right? So what did we really just do here? You've basically just unlocked a new way of seeing and measuring the world around you. This isn't just a bunch of abstract math. It's a genuine superpower. Let's do a super quick recap. If you forget everything else, just remember these 3 words: along, through, and within. A line integral sums along a path, like the wind on your hike. A surface integral sums through a surface, like rain through a screen. And a volume integral sums within a volume, like the charge inside a cloud. Along, through, and within. That's the whole game. By really understanding these 3 tools, you can now calculate total forces, total flows, and total quantities in pretty much any physical situation you can dream up. So the only question left is, what are you going to calculate first? Thanks for tuning in.